It's my pleasure and privilege to introduce Dr. Klaus. He is Professor of Physics at ETH Zurich, Switzerland, and Director of National Center for Competence in Research on Quantum Science and Technology. He completed his PhD at Max Planck Institute for Solid-State Research, Stuttgart, Germany. After postdoctoral studies at the University of California in Santa Barbara, he served as university assistant at the physics department of the University of Munich, where he received the prize of outstanding habilitation thesis. He is a fellow of the American Physical Society, and he received Golden Tricycle Award for family-friendly group management at ETH Zurich. His research focuses on the preparation of ultra-small semiconductor structures with the aim to investigate experimentally new, unusual, and unexpected physical systems, with particular interest in structures that operate at the crossover between classical physics and quantum physics, where several exciting and still unresolved puzzles await their discovery. I want to leave the stage to you.
So it's a great pleasure to be here. Thank you for this kind invitation. You see from my title, there is the word single electron. I understand that this is an audience that has physicists, chemists, hopefully even biologists. And so my goal of my talk is to give you some very basic introduction into semiconductor quantum devices, and hopefully also address some of the basic physics questions in that field. So I also have the title here, Mesoscopic Thermodynamics, and I don't know what about you, but when I was a physics student, I always hated thermodynamics. Thermodynamics is it's old, right? It's from the 18th century, but it's still complicated, and I think there's a real revival of thermodynamics these days. And I think there are many fundamental concepts that we can revisit with modern structures. So let me walk through that, and let me give you sort of a general introduction. So we all have equilibrium, right? I mean, equilibrium is sort of the thing that we can typically calculate. We mostly do not understand things out of equilibrium. It depends how far out of equilibrium. Here's an example, and here is something that we do in our lab, and probably many of you. You take some piece of something, it could be a metal, it could be a semiconductor, you apply a voltage, you measure a current, and the IV characteristic in the best case looks like that. Now, we know in reality it never looks like that if you look in great detail. But we assume most of the time that it looks like that. And now if you fix one of these voltage and you measure the current, and you look in great detail, you see that the voltage and the currents fluctuate. And most of the time, this is a nuisance, right? We know because our measurement equipment has noise, because our cables have thermal noise, and so forth. So all of these fluctuations are things that we typically try to get rid of to get a nice and clean signal. But these fluctuations, depending on what the origin is, can actually contain a lot of physics. And I want to show you a few experiments where we use these fluctuations to learn some very fundamental quantum properties. You know, on top of that, this is something that you can measure with a standard 100 ohm resistor if you measure in great detail. But as things get smaller and quantum devices are small devices where quantum mechanics is relevant, the fluctuations become even more important. And there are certain regions where fluctuations actually dominate. So fluctuations is everything if you make the device small enough. And then you need to understand it. So I talked about a single electron, and let me just give you a general notion on how could we possibly measure a single electron. So let's start out with a capacitor, right? If you have charge, you store the charge in a capacitor, and And here is sort of the simplest capacitor you can imagine. That's from Physics 1 class. And you know that the capacitance is simply the charge divided by the voltage that you apply to these two capacitor plates. Now, if you ask what is the energy it takes to charge this capacitor with the charge Q, it's a very simple integral that you have to use. And you find that the energy is given by the charge squared divided by twice the capacitance. That's what's called the charging energy of a capacitor. And now let's ask the simple question, how big is that energy? And how big is it in particular if this charge is the charge of a simple electron? So we take the charge as the elementary charge, and let's just use for the capacitance something that you can buy in the shop, which is maybe a nanofarad or so. You plug in the numbers and you find a super small energy scale, which corresponds to a temperature of 0.1 millikelvin. And it basically means that this charging energy for an elementary charge is irrelevant. For all practical purposes, it's irrelevant. If you want to make it relevant, look at this equation over here. The only thing you can play with is the C. So if you make the energy large, you have to make the C small. And that is where nanotechnology comes in. So if you make the C small, you get a significant energy that can be larger than this energy scale here. And the interesting thing is, this is a plate capacitor, but of course there are many other capacitors in the world. And you could think of an atom, for example, as a spherical capacitor, with the electrons being one electrode, and with the positively charged core the other electrode. And if you calculate the capacitance of an atom, and you plug it into this equation, you find that the typical energy scales are the ionization energies that you find in atoms. So the energy scales are actually pretty much match what we find for atoms. So this has actually much deeper consequences than is usually seen. So let's plug in numbers. Let's just make these capacitor plates 1 micron, 1 by 1 micron, 1 micron apart. We take this very simple classical equation. So we get a capacitance of 10 to the minus 18 farads. And then you go into this energy equation from before, and then this should be a charging energy that is larger than a Kelvin or so. So if you do the experiment at a Kelvin, you should be able to measure that individual charges charge your capacitor plate here. And then we use nanotechnology to do that. So if you make a schematic of the energy diagram, it looks like that. So this is our small capacitor. This could be a plate capacitor, this could be a spherical capacitor, whatever, it doesn't matter. And this has discrete levels. And these discrete levels, they don't come from the Schrödinger equation. They come from this classical equation that I showed you before, which contains the charging energy. And so basically, you have states here, and this capacitor is now coupled to metallic leads. We characterize them by Fermi energies in the source and the drain lead. So all the states are filled with all the Fermi energies. So if you want to transport from the left to the right, you see that it's not possible because this state is full and no extra electron has space because there's not enough energy. And the next state is too far away. So this is a perfect insulator, and we call this configuration Coulomb blockade. Now for a capacitor, you know that you can tune the charge by adding a capacitive voltage, and that could be some electrode somewhere in the neighborhood, and that allows you to move these states up and down, which you see here. Now we can move one of those states in resonance with the Fermi levels in the source and drain leads, and now electrons can go from source to the dot and up. And by construction, this device only allows one electron at a time. So when an electron has left the source contact, there is no second electron that can come because of this charging energy unless the first electron has gone to the drain. So this is the configuration that we're going to use. This is a schematic here, but it actually describes relatively nicely what's going on in reality. So now let me show you here a device. And I spare you all the details how this device is made and so forth. This black surface is the surface of a semiconductor wafer. This particular one is a gallium arsenide, aluminum gallium arsenide heterostructure. But the same experiments in principle work in silicon, they work in indium arsenide, they work for graphene and whatnot. So you can think of this surface here as containing a sea of highly mobile electrons below the surface of the semiconductor. We use here materials from my colleague Bernadette Scheider, these are ultra pure materials. That means the electrons have an elastic mean free path that is up to millimeters. So the mobilities are up to 40 million centimeters squared per second. These are fantastically clean samples. So you see here, that's the bar is 500 nanometers. So the scattering length of the electron is 1,000 times larger than the size of the device. Now you see these white lines on top here, and the white lines are metal electrodes. And I can apply a negative voltage to these metal electrodes, and then I deplete the electron gas below. So basically you can think of this as an electron can freely move in this plane, except when it starts crossing one of those white lines. And now you see here these small gaps between these white lines, and obviously these small gaps are tunneling barriers, and I can tune the height of this tunnel barrier by appropriate voltages to these gates. Now let's go to a simple configuration where we close off this tunnel barrier here. We close off this tunnel barrier, we close off this tunnel barrier, and this quantum dot, this island of charge, is coupled through one barrier to a macroscopic Fermi seed, to a macroscopic lead. So this is one electron that is coupled to one lead. I would say this is the simplest experiment you can do in solid state physics. And you might wonder whether we can learn something about that. And the interesting thing is we can. So think of it, you have one localized electron that is connected to one lead. And typically, this is not good enough for a transport measurement, because how can you measure a current with one lead? It's a single lead device. You know, the electrical engineers, they're like 3-terminal, 4-terminal, 5-terminal devices. But now we have a single lead device.
Is this acting like a double barrier tunneling junction device? Is there a mechanism?
So if you take this barrier off in the middle and you have a minimum left and a minimum right, then this is actually a double barrier tunneling device. Yes. But now I have just a single barrier. I have a single electron, and the single electron can go in or out.
Why single electron? How do you know that there is?
How do you know that? That's a very good question. So I think for the time being you have to trust me. Okay. And there was a long dispute whether this is really the last electron or not. And it's a very good question because you know this thing is made of a solid. A solid consists of electrons and nuclei and protons and neutrons. In this area we have about 1 million nuclei. All of these nuclei contain electrons, and I'm claiming it's the last electron. So the short story is all the other electrons are strongly localized. They are more than 1.5 electron volts away from this. This experiment is done at 100 millikelvin, which corresponds to 10 microelectron volts. And since all the disturbing processes are exponentially suppressed by e to the minus 10 micro electron volts by 1 electron volt, they're negligible. But experimentally, it took the community at least 5 to 10 years to actually nail this down. So it's by no means a simple statement. Now, how do we measure that, right? So you see here's another channel that is electrically disconnected, because I told you this guy is closed, this guy is closed. So the electrons here on the left, they cannot cross these white barriers. What can happen, however, is that you can send a current through here. And you can send a current through this constriction, and that is determined by the height and the width of this tunneling barrier. And this tunneling barrier is actually close to this quantum dot. And if you have two electrostatically tunable objects, then they talk to each other. So you add a charge here that leads to a repulsive force on the other side. Of course, the further this is away, the weaker this force. But they are relatively close here. And basically what that means, if I add an electron here, it changes the tunneling barrier over here, and that changes the current on the left-hand side. So what I showed you here on the bottom, this blue trace, that's the blue current. So we apply a constant voltage over here. We measure the current, and we measure this current as a function of time. And you see that this current fluctuates between two numbers. And people know that these are typical two-level fluctuators that are annoying and that you try to get rid of. In our case, this is a very nice two-level fluctuator. Namely, when the electron is in here, this tunnel barrier is a little higher, and therefore the current is a little lower. If the electron is out and in the reservoir, then the current jumps up to a higher value. So look at the scale here. This is 1 second roughly. So on the time scale of seconds, we can see how the electron goes in and out of this quantum dot. So we have very nice observation of single electron transport. Now what is this time scale? The time scale is this tunnel barrier between the dot and the reservoir. And this time scale, the device is so stable that it can be 1 electron per day. This is unfortunately not good for a PhD thesis, because then it takes very long to get enough data to get the thesis finished. But 1 second is still a very long time. After all, an electron is a quantum object. And obviously you can make this time scale easily to 1 nanosecond. It's just tuning this tunneling barrier over here. So now what we can do is we can look at this schematically. Look at the quantum dot here. That's this dot, and this dot has discrete states. And these discrete states can be moved up and down by just applying an additional voltage to one of the other gates. So there's a capacitor, so we can move this state up and down. That's this state here. The reservoir here we can treat as a very standard metal. So the metal has a Fermi distribution function, and it has a Fermi energy. And here you see the Fermi distribution function, so this is roughly kT on this scale. That's where the Fermi distribution function is brought in. Okay, on the left-hand side we have a discrete state that we can move up and down. On the right-hand side we have a metal with a Fermi distribution function, and I told you that this experiment is done below 100 millikelvin, so this is actually quite sharp. This is something like 10 microelectron volts. This comes close to the resolution of many optical experiments. So now what we're going to do is we're going to measure this trace here as a function of the position of this energy. And now you can imagine, if I position my energy up here, the state is always empty, because there are no electrons that can jump into the state because it's too high in energy, and that means that the current of my detector will always be at the high state. On the contrary, if I put my state down there, the state will always be full, because the electron cannot go to the right because they are already filled states, and therefore my current will always be low. And as I move through here, I will measure this two-level behavior, but with varying degrees of up and down. And from the calculation of how much up and down current I have, I can calculate directly the occupation, the average occupation of that state. I can also take sort of the up times and do statistics with that, and these are the tunneling times. These are the out tunneling times, and these are the in tunneling times. So we get a lot of information from that. I can also convert this to a current. It's a funny current because it's a current that goes back and forth. You know, a current is just charge per time. And here we have something like 10 electrons per second. It's an interesting number because 10 electrons per second is a current that is 10 to the minus 18 amps. If you buy the best commercial current amplifier that you can get, that's 10 to the minus 15 amps. And that only works when the world is perfect. Here we are 3 orders of magnitude more accurate than the best commercial current detector, and I told you we can go to a day, so we get another 3 orders of magnitude. So this is a current detector that is arbitrarily accurate. The problem is you cannot measure large currents with it because then this time scale gets fast, and our detector is not able to follow it. So it's a detector that has no limitations to the low end, but it has limitations to the high end. Okay. So I told you we can measure the average occupation times, we can measure the tunneling in, the tunneling out times, and we can measure all of that as a function of this energy. Okay, just a flash here. This is a graphene quantum dot because there are a few people here who work with 2D devices. That's a patterned graphene flake, and you can do the same kind of experiment. But I will stick to gallium arsenide here. So now what you see here are the tunneling rates as a function of the position of this discrete state. So here is the plot. Basically, let's look at the tunneling out rate, right? If my electron, my state is far above the Fermi energy, these are positive energies, then I have a finite tunneling out rate, which is determined by the tunneling barrier. If my state is below the Fermi energy down here, then my tunneling out rate is 0 because I can't tunnel into occupied states. That's why this curve goes to 0. And the function that describes that is exactly the Fermi-Dirac function. You can of course do the same thing for the tunneling in rate. If this state happens to be empty, then going from the lead to the dot is just given by the tunneling barrier, which is the same tunneling barrier. But once this is filled, it goes to 0. So you get these two curves for gamma in and gamma out. And if you look at them, there are actually some surprises here, right? They are not symmetric. It's the same tunneling barrier we're talking about, but they are not symmetric. So if you just extrapolate that, you see the extrapolated gamma out rate, this is when only the tunneling barrier matters, is only half of the tunneling in rate. There's a factor of 2 in between. Another surprise is, if the state is in resonance with the Fermi energy, the two rates also differ by a factor of 2. And they match exactly each other at some finite energy. So what is going on here? So if you look at a single electron going into a quantum dot, then we know this quantum dot has one state. But because of Pauli principle, this state is twofold degenerate. There's a spin up and a spin down version. So the electron has no defined spin when it comes from the reservoir. So it has 2 landing spots. So it has a tunneling barrier, and on the other side there are 2 landing spots. Now, however, on the other side, once the electron is in, it sits on one of the 2 states. It has a specific spin. And there's one possibility to get out. And that's the reason for this factor of 2. That's why the tunneling in is twice as likely as the tunneling out, because you have a degeneracy of 2. Now, nobody is surprised in this audience that an orbital state has a spin degeneracy of 2. The funny thing is that this has not been demonstrated before. And it's not so easy, actually, to measure degeneracies of quantum states. There are some techniques in optics, but in transport we typically don't do that. And again, for the 2D people, this is a very interesting concept, because in the 2D materials there are valley degeneracies, there are spin degeneracies, there's orbital degeneracies. Some of them are highly disputed in magnetic fields and so forth. Here's a way how to measure them. And that's actually what's happening. So we found that an electronic state is twofold degenerate. No big surprise, but with a very simple experiment we get some very deep understanding of quantum mechanics. Okay, now there's something else which is interesting. Look at this crossing. Where do the 2 curves cross? They cross at a finite energy. And now you can calculate this energy. It's very simple, because both of these curves, the blue curves, are Fermi-Dirac functions. One is for the empty states, that's Fermi-Dirac. For the full states, that's 1 minus Fermi-Dirac. Here is the tunneling probability. So you know all of these curves. So there, you set these 2 equations equal to each other, and you calculate what this energy difference is. It's just a simple rate equation model. And this is the energy. It's kT times logarithm 2. Now, I'm not sure whether that rings a bell for some of you, but that's a very important energy. So Rolf Landauer was a theoretician at IBM some 10, 20 years ago, and he asked a very fundamental question. What energy does it take me to erase a classical bit? And he did a consideration from only entropy arguments and information theory arguments. He did not consider physics, he just said, what's the minimum energy I need? And that's this number, kT times logarithm 2. So that's sort of the classical limit for the operation of a classical computer. Our computers are actually 5 orders of magnitude above this. So this is not a relevant limitation for our today's computers. But this is a fundamental limit, and it's typically very hard to measure for obvious reasons. There's something similar for qubits, but I don't want to go into that. So somehow this is the same energy. Why is that the same energy? Well, now you can look at the system from a different perspective. You could say, if my electron sits in one of the 2 quantum states, I have a bit. If it is between in and out, which means that the occupation probabilities are the same, which is exactly this point here, then I have erased my bit, because I don't know where my electron is. So I could argue from an information theoretic point of view that where these 2 rates are the same, this is exactly the point where I have lost all of my information where the electron actually is. And that's why we have access to this very fundamental energy scale. So again, simplest experimenting on physics, but there's some interesting twists to that. Now, here you see you can do rate equations, orders of magnitude. The fit is the degeneracy of the state, and it's no surprise. Now, let's look at 2 electrons, right? 2 electrons is a little different. So let's take a system that contains 1 electron, and then the second electron can go in and out. So on the left-hand side, that was our first electron. These are the rates. These are the possibilities to go in and out. The second electron is different. You see, the first electron is already in. So the second electron that's coming, that just sees one option to go. There's one spin state empty. On the other way, however, we have two equivalent electrons. And we know quantum mechanical particles are indistinguishable. So any of those two could go. So you have two options to go out and one option to go in. So basically, if you look at the rates, the green rate is twice the blue rate. For two electrons, it's now the opposite. The blue rate is twice the in rate. Roughly, not exactly, but roughly. And then you look at electron number 3, it's reversed again, electron number 4, 5, 6, 7, 8. So there's an interesting way of looking at these degeneracies as you fill your system. And you know that this breaks down in the periodic table because of Hund's rules. This breaks down as soon as exchange effects become important. And so we tune the system that it behaves properly, but most of the time it does not behave properly, or I should say, in other words, it behaves in a more interesting fashion because interaction effects become relevant. Okay, now let's go to another experiment, which is very simple. Now we close this tunnel barrier and that tunnel barrier, and we just have two quantum dots. That relates to your question. So you have one electron, two quantum dots. And the electron can be in the left one or in the right one. We still have our detector here, and this detector can tell us where the electron is, because depending on where it is, it's closer or further away from my tunneling barrier, and I can detect that again with my current down there. So the current down tells me electron is on the right or electron is on the left. And it looks schematically like that. I have my electron on the left, that can tunnel to the right, or right, and it tunnel to the left. And now this game with the degeneracies is over, because both states have the same degeneracy. So now tunneling from left to right or right to left should be the same if the states are in resonance. So let's do the experiment. So I don't show you all of these noisy fluctuating curves, but just the analysis of these curves. So these are the tunneling rates as a function of energy, and the energy here is the energy difference between these two states. So if this energy difference is 0, the two states are in resonance, and blue and red means left to right or right to left. And you see that the two curves fall perfectly on top of each other. So it confirms what we have expected. Now let's add a second electron. So now we have two quantum dots and we have two electrons in our system. And now life becomes more complicated. Why is it more complicated? Let's assume we have one electron in the left dot and one electron in the right dot. Now you know, if you want to bring the right electron to the left dot, there is this Coulomb blockade phenomenon. So there's an energy that you have to pay. So the second electron comes to the same location as the first electron. So either this is what we call a 1-1 state, and this is what we call a 2-0 state. The overlap of the wave functions is very different. So the two configurations are by no means equivalent. So let's look at just the current trace. This is our detector here. We monitor this detector as a function of time. And it looks really funny now. Look at this. Nothing happens. Electron is stuck. Then this goes up and down. That means an electron goes back and forth. And then it gets stuck again. And then it goes back and forth. And then it gets stuck again. So what is happening there? This is what we call spin blockade. And it's spin blockade visible on the level of individual electrons. This phenomenon has been seen by many people before. There's a wonderful paper by Kabucha from Tokyo, but it's not seen on the single electron level. So what is happening is the following. You see, you have two electrons in the same dot. Now these two electrons, they can have opposite spin, or they can have the same spin. It's not exactly true what I put with my fingers here. We should call it a singlet and a triplet, but the real singlet wave function is hard to show with my fingers. So let's just say, if the electrons have opposite spin, they sit in the same orbital state, and therefore they are low in energy. The triplet costs energy, because the triplet means that there is additional exchange energy, and the two electrons sit on different orbital states, and that costs energy. Now this electron sitting on the left has a specific spin, whatever it is. Another electron coming has to have the opposite spin. If it has the same spin, it has to go to a higher energy state, which is not accessible.
Okay, so if it has the same spin, it goes to the left. And then it goes back. So that's what's happening here. Electrons have opposite spin, and so one electron moves back and forth. Now, if for some reason the spin is flipped, and these two electrons have the same spin, then nothing can happen, and the situation is blocked, and there's no transfer, spin blockade. So now we have to ask ourselves the question, what flips the spin? Spontaneous. The system is isolated, there's nothing happening, no coupling to the environment, but there are still other spins in the system. There are nuclear spins. The whole material consists of gallium and arsenic atoms and aluminum, and they have nuclear spins, and it's possible that this electron spin flips its spin, and the corresponding nuclear spin flips its spin by hyperfine interaction. This is a very weak process, but it can happen. And that could lead to these other time constants. Another possibility is spin-orbit interaction. After all, this is a motion in real space. The electron goes from left to right. And if you have spin-orbit coupling in your material, and all materials have to find spin-orbit coupling, that means if you move in real space, your spin always flips a little bit. It might not flip enough to go the other way around, but if you do it often enough at some time, it flips. And so we have two mechanisms here, hyperfine interaction and spin-orbit interaction, that can limit this process over there. And these processes are known and investigated, and one can have a closer look into that. And one can measure now the directional dependence and measure a lot of the microscopic properties of the system. I don't want to go into the details here, but just give you the flavor that this simple experiment allows you to measure very fundamental properties.
Now what I show you here is the same that I showed you for one electron, now for two electrons. So blue and red means left to right and right to left. So far what I've shown you previously was the spin blockade. Here I show you the rates. And here is again, that's the energy, but zero means the two states are in energy. The two electron state on the left is resonant with the 1,1 electron state of the entire system. And you see there's a factor of 4. But why is there a factor of 4? That's again very simple, because as I told you, there are singlets and triplets. If the spin doesn't matter, and the two electrons are on opposite sides of the dot, they can have arbitrary spin configurations. It could be a singlet, it could be one of the 3 triplets. So there are 4 configurations that you can tunnel into. If you go from right to the left, you can only have a singlet, and that's constant. And that's why the ratio between blue and red is 4. It's 4 states versus 1 state. So it's the relative ratio of the degeneracies of these two states. Okay.
Why cannot you destroy these degeneracies by applying this magnetic field?
Yes, very good question. So the magnetic field is a very important parameter here. And if you go to a high enough magnetic field that you split the singlets and the triplets, these two degeneracies become the same. Yes, thank you. I also didn't mention here that we always apply a small magnetic field to overcome the nuclear magnetic field coming from the hyperfine interaction. I neglected that here. Yeah.
So in the previous slide, you had 2 time scales. Can you relate those time scales to the strength of the interaction?
Absolutely, yes. So the fast time scale is the tunneling rate, and the slow time scale is the spin flip rate. Yes, and the spin flip rate in our case, whatever it's mentioned actually here, this 30 millitesla are applied to eliminate hyperfine processes. So we are only left with spin orbit processes, and this is the spin orbit spin flip scattering time. And you see it's interesting, it's seconds. Yeah. So if we dream about spin qubits and quantum computers, it's not so bad. And actually, meanwhile, we have learned that the spin orbit interaction depends on the k vector of the electron. And if you can position that, because it depends how you arrange your double dot system with respect to the crystal lattice. And there are directions where you compensate for spin orbit interactions, and you can make that ours. So if you understand enough of the details of the system, that works. So yeah. So why do we do that, right? Because we want to build a quantum computer. I think most of you guys probably want to do that too, in some way or another.
And you might think that this is hard, right? It's actually not that hard, right, if you think about it. It's you have to prepare a quantum state. I've shown you how we can do that. You have to manipulate it. I've not really shown you how to do that. And you have to read it out. And now I typically make a political joke, but this is not so easy today. So I show you a German joke, right? So this is a quantum state, right? You probably know it. It's strongly coupled to the environment, right? And there are many people who would like to manipulate that state, right? And you think it's hard, but it's not so hard. You can do a pair with 2 poles, and you have manipulated your quantum state. And there is a technical term, which is privacy amplification, which is also relevant. It comes from quantum security. It's here not very helpful. But then, you know, we have decoherence in our system, and you have to work relatively fast, so you need to do a single shot read out and then turn this on. Okay, so back to physics. I told you at the beginning about thermodynamics. And thermodynamics is at the very heart of what I have just told you. It's about fluctuations and how we can live with these fluctuations and whether we can use them. And I want to show you 2 simple experiments. So that's a macroscopic experiment, right? You have a resistor, a voltage, a current. You know that it produces heat, and the heat is dumped into the environment. And you would love to do the opposite, right? You take the environment, you take the heat from the environment, and you drive a current. And you all know it doesn't work because of the second law of thermodynamics. But this is a macroscopic statement. Macroscopically, the entropy is actually fluctuating. That's not a constant property. So let's have a look into that. And there's a very interesting theorem on that. This is the fluctuation theorem, and it states the following. If you have a system that is coupled to the environment, then it can dump entropy in the environment. We can get back entropy from the environment. And the probability of getting or dumping entropy is simply given by this exponential curve, the change in entropy divided by Boltzmann's constant. It's a fantastic theorem. It's not based on any experimental system. And it has been modified, it has been confirmed, for example, by people who look at beads in spheres in liquids and monitoring how these spheres behave in an electric field. And of course, when the beads are charged, they move in an electric field, but not all the beads do that. Some of them are under Brownian motion and they go the wrong way. On average, everything is fine. But for the individual bead, this might be different. Okay, now of course, you want to do that electrically, and you put in some numbers. You say our resistor 1 volt, 1 amp, you calculate the heat, you calculate the entropy, and you find, well, it's completely unlikely that this exponential factor is so big that you can completely forget the processes that go in some sense backwards in time. Now let's look at our conductor. We can control individual electrons. So now let's say that's the probability that n electrons move from left to right. That's the probability that n electrons move from right to left. And we take this equation from before. So remember, that was the change in entropy. The change in entropy is the heat that we dump in one of the systems. That's the number of electrons times their charge times the voltage, divided by Boltzmann constant, that's the entropy change, and divided by temperature from this exponential function. So if you look at this function, it's actually quite simple. Let's assume we are in thermal equilibrium. So no voltage applied to our system. And you see this exponential is 1, and the 2 probabilities are the same. So that's fine, right? If you're in thermal equilibrium, it's equally likely to go from left to right than from right to left. On the opposite regime, if you apply a huge bias, so which is much larger than kT, then you see, okay, one probability is much larger than the other one, and that's our classical expectation that we always move in the same direction. And the interesting regime is, of course, in between, when the applied voltage is of the order of the thermal energy. Okay, let's do that experiment. But now we need a little more. We need not only to know where the electron is, we need also to know where it goes. We need directional information. So we take 2 quantum dots, source, left dot, right dot, drain, and down here is our detector. And here you see our
charge detector, and the charge detector now fluctuates between 3 levels. There's a down level, a middle level, and an up level. That means electron is out, left or right, out. It's in the left dot or it's in the right dot. And because we have now 3 levels, we can tell which direction the electron went. So the up level means the electron is on the left. Then down means it's in the left dot, then it's in the right dot, and then it's out again. So if you have a sequence like that, we know an electron moved from left to right. Now if you have something like that here, that means an electron goes from right to the left dot, back and forth. But that's not what we care about, because that is just electron charge moving back and forth. What we care about is an electron going from here to here, or from here to here. And if you have a trace like that, you can get this out. So here's a long trace. You take this trace, you chop it up into intervals, and each interval you give to the computer, and the computer gives you an n. It says for this time interval, 5 electrons went from left to right, or 2 electrons went from right to left. So you can do a diagram that says my probability to have a certain number n as a function of n. So such a trace gives you such a distribution. This trace was taken with no applied bias in thermal equilibrium, and so you see very nicely this is a symmetric curve. On average, we do not transport any charges, but there are intervals where we transport charge from left to right. These are positive ends, and there are other times when we transport charges the other way. But on average, you see it's a symmetric distribution. Now you do the same distribution, but now you apply a bias. So that's equilibrium, that's a small bias, and now you see the distribution has shifted. And of course it shifted because electrons have to flow in the direction of the bias, but you see there are still a few events that go the wrong way. So these ones here, in some sense, they are in the opposite direction than the one that you expect in a macroscopic experiment. So we have this data now. Now we can compare to theory. And let me remind you of this fluctuation theorem. That's this exponential here. So this data down here, that's the logarithm of the left-hand side of the equation. That's the vertical axis. The horizontal axis is the n. Everything else is fixed in our experiment. We know E, we know V, Boltzmann constant, temperature, everything is known. So you see, here is the experimental data, and that's the straight line. So it sort of fits. It fits by 20%. So what is the reason for this 20%? That's actually something that you also know. This is perfect life. Well, in the experiment, life is never perfect. And the reason is that first our detector misses fast events. You know, tunneling is a stochastic event. So if you say my tunneling time is 10 microseconds, that doesn't mean that every electron tunnels every 10 microseconds. Some are faster, some are slower. There's a distribution, and 10 microseconds is the time constant. So there are many fast events that we miss because our detector is not fast enough. But there are also slow events that we miss because our experiment has a finite time scale. But these are not unknown parameters. We know the bandwidth of our parameter, and we know the time constants of our parameter. So we can actually calculate statistically how many events we miss because of experimental limitations. And we can put that in, and then we get the dashed line, and that fits very nicely into the experiment. So all of this put together, now you can play with the temperature, you can play with the bias and so forth. And that means that this experiment gives us a very nice access to these fluctuation theorems that play a role in thermodynamics on the level of individual events. Okay. Now let me, yeah.
You are missing like some events, but you are taking the ratio, right? So I felt like the ratio should be the same. But I see that your curve, recalculated curve, actually is. That's good.
I've never thought about it in that way. I think if the ratios are the same, I think the effects should cancel out. But if they're not the same, and that is the regime in which we're looking here, they don't cancel out.
So, like, if you go like fast event, in the case of fast events, the ratio of left to right and right to left are different.
Yes.
Yeah. Okay.
So both are Poisson distributions,
Okay.
but the Poisson distributions are shifting, but the cutoff is the same for both distributions. So I don't think that it cancels out, but
But if it's not cancelled out, how will it come perfectly Gaussian?
well, it's a Gaussian within experimental limits, right? I mean, a Gaussian would go even further here. There are tails that we cannot measure. These are sort of the rare events that are not on the distribution.
But they are perfectly symmetric.
Yes. This one is symmetric. This one not. So actually the theorem is interesting. The theorem doesn't tell us anything about this distribution. It just tells us what the mean does. I have not seen any theory that tells us, for example, the width of this distribution is also not in that theorem. And I think there's a lot of interesting physics in that distribution that we haven't explored yet. And one of them is how it falls off, and the width, and the symmetry, and so forth.
Because I presume that would be asymmetry.
Yes.
In a pyramid system.
Yes.
Should be.
Yes, I agree with you. Yeah. Okay, so let me come to the last point, and that is the Yarczynski relation. So the Yarczynski relation was invented after I had studied physics, so it's a good excuse for me that I didn't know about the Yarczynski relation. But all the younger people should know about the Yarczynski relation. And he's actually a nice young professor, so I thought this must be an old man, but he's healthy and alive and still full of energy. So this is a very interesting relation. This is a paper that is very highly recommended to you. It's, again, pure theory, it doesn't relate to any experimental system. And he asked the question, we all know it's hard to go out of equilibrium. But can we predict what's happening out of equilibrium by measuring equilibrium properties? Because that is something that we know experimentally and that we know how to do theoretically. And this equation that you see here is the following. If you have two processes, two states, and you go from here to there are many ways how you can go from here to there. But you know where these energies are. So if you are out of equilibrium, that's sort of the work that you have to invest to get out of this equilibrium. And then you average of all this averages, or averaging over all the processes that bring you from here to there, whatever they are. This is the same as the exponential of the difference in free energy of the two states in equilibrium. So the right-hand side of the equation has quantities in equilibrium, and the left-hand side has quantities out of equilibrium. So that's a fantastic relation. As far as I know, there are only 3 experiments that have verified that. One is a very interesting experiment in biophysics, where people have looked at charge distribution in DNA. That's very fascinating. Another one is using superconducting qubits, and the third one is this one. So how could we play with that? How could we access non-equilibrium physics? So, of course, we use quantum dots, you're familiar with that. And now, in order to get out of equilibrium, you apply an additional voltage here. So we apply a voltage here to this gate, and you remember this gate moves the state up and down, and obviously if you move it fast and you move it high, then we drive the system out of equilibrium. And since we know the time constants of the system very well, we know exactly when we're in equilibrium and when we are out of equilibrium. Okay, so what you see here is the time. That's our drive, that's the blue curve, and that's the voltage that we apply here. So we go from the low state, then we move up quickly, quicker than the tunneling time, because if you move up slowly, then of course the electron will tunnel at the right point, and then everything is in equilibrium. So this time scale, the rise time has to be quicker than the relaxation time of the system. Then we wait, and then we do the same thing in the reverse direction. And now, here are the numbers, they are not so relevant. So we move up here. That's an application of this part here. So the energy in the system moves up on some scale from left to right. Now what does our detector see? Let's assume our state is filled, and now we move above the Fermi energy, so at some stage we lose the electron. And if you move quickly, the question is, when do we lose our electron? And here is a possible outcome. So you see the red traces the detector, that means the electron is in, and at some point it leaves. And you see here, that's the time when it leaves, and that's not at the symmetry point, because we are out of equilibrium. That's one experimental outcome. Another experimental outcome, So here you can see when it leaves, and that allows you directly to measure the energy dissipated in the system. So you move your electron above the Fermi energy, then it leaves, and then it has to get rid of each energy. So you measure Q directly. And you also measure delta U, that's the energy before and after the system. So you know delta U and Q, and you can directly calculate the work invested in the system. It's all in this data. But this is only one possible outcome. Let me show you another one. What could happen is that the electron leaves, comes back, leaves again. So you see the initial and the final state are the same. These are the equilibrium states. But what has happened along the way is different. And obviously for each of those processes you can do the same analysis that I just showed you. You can calculate what is the dissipated energy, or actually here you get energy from the environment, and you can calculate the change in internal energy. So you know all of these numbers. And remember, in this Yarczynski relation, we wanted to do statistics. We wanted to go from here to here by all possible means. And this is one way, this is another way. Here you see the calculation. Here is still another way, nothing happens at all. There are many different processes. You do the experiment and you average over all of them. So you get the left-hand side of the equation. Here's still another one. You see initial and final states are the same, but the electron has left and came back again. So there are many different processes and we can all measure them. So now, for each of those processes we get the delta W. We calculate this exponential. And because we have many events in the experiment, we can do an average over them. So that's the left-hand side of the equation. Now how about the right-hand side of the equation? So we know that we can calculate the change in free energy by these partition sums. And these partition sums are simply given by the energy of the state over kT, and you see here in front is the D, the degeneracy of the state. And that brings me back to the beginning of my talk where we measured the degeneracy of the state. So we know exactly what this D is. So we know the D, we know the T. We can measure the energy of the state because that's our voltage. So we can calculate these partition sums and we know what the change in free energy between initial and final state is. So we have experimental access to this part and we have experimental access to this part. So let's put this all together. So on the left-hand side of the equation, you basically see this curve as a function of the energy of the state. So for one energy, you would get 1 point. We do this experiment for many different energies of the final state. That's this parameter here. And the theory gives us this curve here, and you see the experimental points on that. So it's not so easy to interpret this curve as it is drawn here. And maybe you can just take away that the theory and the experiment fits together. And there's a lot of deep thinking behind that, why this equation actually holds. It's by no means obvious that it holds, because you're comparing very different quantities of your system. One is something where you just put your system in a few quantum states and you know what they are and you calculate the free energy. And the other one is where you do a lot of driving out of equilibrium and you compare these two, and if you do it correctly, you get a nice answer. So this is very interesting because this theorem holds also not in classical physics as I've shown you here. It also holds in quantum physics. And then it becomes very relevant for the operation of qubits, because qubits need to be driven, right? Otherwise you cannot operate a quantum computer. And if you drive a qubit, possibly out of equilibrium, you need to know what this means for the energy. It's not even clear right now how to define quantum mechanical work performed or done on a qubit. So there is a lot of interesting physics in there that needs to be explored in order to move this to the real quantum world. Okay, now just a few slides again for my friends for 2D systems. It is possible to do the same thing with bilayer graphene in a way that you encapsulate bilayer graphene between boron nitride and apply a vertical electric field and open a gap. This is what people known for a long time, but now you can actually use it to build quantum devices. And the trick is to use a graphite backgate and use an additional top gate to basically open a band gap and then locally position your Fermi energy in and out of the band gap to create exactly the same devices that I've shown you for gallium arsenide and bilayer graphene. And this actually works. This is a fantastic system, and I expect that this will work actually much better than gallium arsenide because it's much thinner and you can make it much smaller and you can make much more strongly coupled quantum devices. So I think that's something for the future. So let me conclude here. I showed you a couple of experiments on playing with individual electrons. I think individual electrons contain a lot of nice physics, and it's fairly straightforward to understand. And it contains interesting properties about tunneling rates, about degeneracies, about spin conserving and spin flip tunneling. You can learn something about nuclear spins. You can learn something about spin-orbit interaction. And you can use that to optimize your spin qubit if you want to have log operation times. And then there's this whole, I think it's a new field that's starting. This is sort of extended classical thermodynamics, but there's a new field called quantum thermodynamics, which is very exciting, and it's not only here for semiconductor devices, it carries over to ion traps, to superconducting qubits, to atomic systems, where we need to understand how thermodynamics actually plays a role on the level of individual quanta. I should mention here in particular Andrea Hoffmann. She was the PhD student who did most of this work, and Willy Meisi was a postdoc who was also very important. So thank you very much for your attention.
Thank you very much for this very, very interesting talk. Let's have questions from the audience.
Question, but if you could go back to this part where you mentioned the coupling effect, it was
This one here.
yes. So, if you consider making these, since you also mentioned to the version of these, if you consider using tungsten disulfide, the spin orbit interaction there is much more stronger. So, I'm not sure where it will lead, but have you considered?
Yes. So there are two answers to that. Spin orbit is good and bad. It's bad because it leads to decoherence, but it's good because it allows you to manipulate spins. Now, I have watched this field with the TNPCs for the last 5 years. The problem is if you come from a quantum transport point of view, these materials are lousy. So they have mean free path of the order of 10 nanometers, and none of these experiments is possible. This has, I think, changed within the last year. Tungsten diselenide we are trying, but it's still on the 10 nanometer scale. But molybdenum disulfide has not as strong as spin-orbit interaction, but stronger than these materials. And we have now made the first quantum dots on molybdenum disulfide, but they contain about 100 electrons. So we are still far away from the last electron. So I'm very sure that this will happen in the next 5 years. But it's not clear
Which requirement there is having a long
yes. These materials are good for optics because you have localized states, but for transport, it's just an omni conductor that diffuses. Yeah.
Any other question? I have just a comment. Like, I agree that everyone should know Jarzynski equation. It's actually one of the projects that I'm giving the course, and people should relate like computational thermodynamical processes and show that this holds.
If this doesn't hold something.
Yes, yes. Okay, then let's thank, yes, there are some people from my course there smiling. Let's thank the author again.
folds all the way. They are distribution functions that change the so I would argue you're completely out of that.
Yes.
But what makes it go even more out of that? Yes. So we haven't explored that a little bit. The problem is that these time-dependent voltages and time-dependent voltages they couple. So you get it's not it's just experimentally induced. Either over many particles, or it is for one system that the average over many iterations.
Well, I think the last experiment that I showed you really tuned it quickly, so that the system followed it right. That's not the This is poster here.
Yes. One.
Thank you.
I thought that you were asking 1 or 4.
No, this is the poster that I saw.
Sorry. I think it's because of your presentation. Like 1 or it's stuck.
Now we're going to read, right?
Yes.
So I can't reach the program now, but
After meetings, free time.
yes.
Yes.
So maybe you can call me. I can come where.
Or I can bring him here. I can bring him to your office.
Thank you for we can yes please.
Okay.
So we will meet.
Yes.